one, you'll see the first differential equation will be y1 dot equals y2. y2 dot is minus g over L y1. And when I go to the nonlinear one, the first differential equation will be exactly the same, but instead of having a y1, I'll have a sine of y1. Okay? And again, this is what MATLAB needs. It has to, it requires you to write a routine that will, given the values of t and the y's, calculate dy dt. Okay. So let's look into that. Okay. Let's see where I put that thing. Oh, simple pendulum. Okay. Simple pendulum linear. Let's look at that one first. Okay. And again, I'm going to use the ODE 45, and you know the syntax of that. Okay. So now we're going to use it with two differential equations as opposed to one. So simple pendulum versus what? Is this the linear or the nonlinear one? I can't see. Linear. See, I called it simple pendulum linear. You see at the top? Okay. So, what does this thing have to do? Just like all the other things that we did with differential equations, you give me a bunch of t and y values, it has to calculate y dot. Okay, but now y dot has two components, right? There's a y1 dot and a y2 dot. Okay. So the first thing I do, this was a pain, I know why MATLAB makes you do that. I tried this without this and it didn't work. You have to just tell y dot is, you have to tell it's a vector. So I said y dot is zeros 2 by 1. All that is telling MATLAB is that I'm going to see a y dot sub 1 and a y dot sub 2. There's going to be two elements in the vector y dot, right? So if it was like three differential equations, you'd have y dot equals zeros of 3 by 1. The zeros is just take memory and tell it it's a vector. It doesn't matter what you put in there. It's putting 0 in there, but I'm going to be filling it up with the right value immediately afterwards. Okay, so let's look at the first equation. Y dot of 1, that's this guy. What is it? It should be y of 2. See? That's exactly what you have over here, right? Okay, and what's y dot of 2? I guess I took L equal to 1 and G is 32. So I got y dot of 2, it should be minus G over L, which in our case is minus 32, times y1. That's the linear version, okay? Stupid thing coming up. And I guess over here, again, these are simple enough that there's no vectorized code that you have to write, but again, think of t and y as vectors, okay? Matthew even told me, this is very interesting. See on the t has that little thing over it? Let's see what it says. Argument t might be unused. Yes, because it comes out that in the pendulum problem, it's called an autonomous equation, the derivatives for y1 and y2 are not explicitly functions of t. But the integrators are meant for the more general problem, so you always code it up on the right-hand side, t and y, okay? So that's more of a warning than an error message, okay? It's saying, hey, MATLAB looks at it and says, you gave me a t as an input argument, you never used it, okay? So sometimes that would be a good thing to say, oh, I made an error. But here there is no error because the derivative does not depend upon t explicitly. Okay? Now let's go to the other one. I think you can anticipate what that's going to be. It's going to be called simple pendulum, and it's going to be nonlinear t and y. Okay? Everything will be the same except this guy is going to change. Instead of minus 32 y1, it will be minus 32 sine y1. But you have to code them up separately because you have to be careful to tell MATLAB, am I using the linear form or the nonlinear form? Okay. Let's go to that one. Simple pendulum nonlinear. There we are. Again, same exact. I just changed one line, right? Look at y dot 2, and now it's minus 32 times the sine of y of 1. Okay? And remember, it's a function, so you have your end statement and all that, and the same thing again. There's two simultaneous differential equations. So there's a y dot 1 and y dot 2, which in MATLAB is y dot of 1 and y dot of 2. Okay? So it has everything it needs now to calculate the derivative, either in the linear case or the nonlinear case. Okay? Now I'll just quickly go over the driver that I wrote for this. It's a script, okay? And I'll tell you what I did. I think it'll be pretty transparent. I called it drive pendulum.m. Okay, this is kind of the main program that's going to drive everything. Okay. Okay. The first line you shouldn't concern yourself with is that when it integrated and I looked at the results, I found out that the curves weren't smooth. So there's an option called Refine that you can use for the OD solvers that will make it more smooth. But you know, don't pay attention to that. That's just more to make the graphics prettier. Okay? So let's see what happens over here. Okay? I'm setting my T0 to be 0 because I'm going to start the simulation at T equal to 0. T final is 5. I guess I'm going for 5 seconds. Okay? And remember the T-span, that 2-element vector? The first element is the initial time, and the final element is the final time. Okay? Clearly, I just could put T-span equals 0, 5. Okay? But sometimes you want to, change things. This way, you only have to go back to the initial assignments. Okay. Very important now. Okay? What's in y of 0? Okay? Let's think about this. Okay? Look at the y vector. The first element of y is the angle, and the second element of y is the angular velocity. So when I have basically y0, I'm saying what is the value of y1 and y2 at time equal to 0. It's a second order differential equation, so I need two things, right? The initial angle and its velocity, which now basically correspond to y1 and y2. So what did I do? So for the initial value of the angle, I put 15 degrees. Notice I multiply by pi of 180, okay? Because it's in radians, everything's in radians, okay? And then, what I do for the velocity, 0. So the first experiment that I'm doing is I'm taking the pendulum, pulling it to the right 15 degrees with 0 velocity and just letting it oscillate back and forth. Okay? That's my first experiment. Okay? And then, I'll just quickly go through this. First, I use the ODE solver to get the linear solution. That's why I called it T-lin, Y-lin. That's to remind me that the output of this solver now is the linear version of the problem. So you got ODE 45, right? Okay. Now, of course, I have to use the routine called sim pendulum lin. That's the first one I showed you. Okay. T-span, we know what that is. The initial value of y, and forget about options. That's the thing for the refined. Okay. Normally, you won't need options. Okay. Okay. So the ODE solver hopefully does that. And the vector T-lin and Y-lin, what does that have? If I plotted that, that would be the solution to the pendulum problem if I use the linear version of the equations, if I use this guy, right? And then the next thing is I just use the nonlinear, okay, and do the same thing, okay? And then I plot out, and we'll see a co-plot, because I'm plotting vertically. Notice I do T-lin, Y-lin of very important over here. When I come out over here, with T-lin, okay? Let's say that has 100 elements. It'll be 100 by 1. When I get with Y-lin, if you look in the Who's thing, that will be 100 rows by 2 columns. Why is it 2 columns? The first column will be the angle, and the second angle will be the velocity, okay? Because remember, we're asking it to solve a system of equations, so MATLAB's going to come out for a solution for Y1, which is the angle, as well as Y2. And the way it does it over here is that this guy will be a matrix. Okay, the number of rows will correspond to how many time points that you have. The first column will be the angle, and the second one will be the derivative, which is the angular velocity. And what I want to do is I just want to plot the angle itself. So notice what I do. I plot T-lin, Y-lin, first column. Remember the colon thing? Everything in that matrix, the first column. Then, what do I multiply by 180 over pi? So that I can convert it from radians to degrees. Because remember, I had 15 degrees. I'd see things in degrees like most people, okay? And do the same thing. T nonlinear. Now, TNL may be of different dimension than T linear. Maybe when the OD solver tried to do the nonlinear equation, it found out that it had to use many more points than over here. So the dimension of this guy and T-lin will be different, but the Y nonlinear, YNL, will have the same number of rows as this. And again, the first column will be the angle, and that's what I plot, and the second angle will be the angular velocity. Okay. Okay. So we'll see that. Then, the rest is exactly the same, but what did I do? I just changed one thing. I now pulled it to 60 degrees, right? So you can see basically the first one, the second one is a larger angle than the first one. I think the first one I used, 15 degrees, right? And you'll see that 15 degrees, at least for t equals 0, whatever it goes, 0 to 5 seconds, they're pretty much in phase with one another. But when I make the angle 60 degrees initially, you can see a large deviation, okay? So again, when you ask the question about you know, when can I get away with the small angle assumption? What we'll see from this is that it's not that simple. How much time are you talking about? Because believe me, what you'll see for the linear, you'll see for the case of the 15-degree initial displacement, when I go 5 seconds, they overlay. But believe me, if I went further in time, they wouldn't, okay? Just they get out of phase at a slower rate. So in answering that question, it's not so simple about, oh, if theta's below this threshold, you can use the linear. No, it depends how much time you're talking about also, because there's always an error in there. It builds up over time. Okay, so you should look at this routine. Also, I'll put up on the website, okay? And again, it's exactly the same coding as the other one, except that it just redid it for 15 degrees and went to 60 degrees. Okay, let's just run it, okay? So I got everything that I need. Okay, you'll notice basically that the thing that I have to run is the script drive pendulum.m, this guy. And it's gonna call the ODE solver with both the linearized version and the non-linearized version. Just clear everything also. Okay, everything is clean now. Okay, drive pendulum.m. Okay, let me try to just run that. Go over here, run. Should get 2 graphs popping up, right? Okay, let's look at the first figure, okay? Let's see what we have over here, okay? It says initial displacement 15 degrees. Yep, that's the one that I did. And you notice it's equal to 0, 15 degrees. I got a little legend over there. Let me move that over because it's on the plot. Right. So the blue curve, okay, corresponds to the linear equations, and the red curve corresponds to the nonlinear. And you can see basically that it's already starting to get a deviation near 5 seconds even, right? But if you're interested in 0 and 5, you can say, the linear solution rather is pretty good given this initial displacement of 15 degrees. If I went further in time, then they start to deviate more. Okay? So let's do the same game again, okay? The other case was what? I went again from 0 to 5 seconds. Instead of having an initial displacement of 15 degrees, I pulled it to 60 degrees. And that's the second graph. Okay. Initial displacement 60 degrees. Yeah, I go to t equals 0. They're both obviously they start off the same, 60, right? Look at this already. See how they get out of phase in 5 seconds. Okay. So again, this is a good way of assessing whether you need a linear version or a nonlinear version. Okay. Again, a very simple problem, but at least it can illustrate to see what's going on. Okay. What else I can say? Not too much more you can say about this. Okay. And probably if I use the initial angle maybe 1 degree, I probably could run it for maybe 500 seconds before you saw anything different. Okay. And again, the mathematics kind of suggests that, right? Because we're replacing sine theta by theta, and we know that the Taylor series, next guy is theta cubed, and yeah, if theta's small, that's going to be kind of negligible compared to theta. But if theta starts getting large, in theta cubed and your theta are not, theta cubed is not negligible compared to theta. Okay. Okay, that pretty much does it, okay? And the thing which, again, what I want to emphasize, and I think we'll probably stop here ready to go to the next topic, okay, is that when you want to solve a second order equation, you have to write it, and you want to do it by MATLAB, you have to write a system of 2 first order equations. If you're going to solve a third order differential equation, the same thing. And again, it doesn't matter how complicated they are. So long as you can isolate the highest derivative, you can do it in MATLAB, okay? Okay, so we've got the homework here, and I guess we'll continue on Wednesday with the next topic.